on that. Sometimes you have a continuous time signal. Now, an example of a continuous time signal is when you make a radar experiment. When you have a radar experiment, radar is when you have to measure the time of delay. So the time of delay is continuous by nature, and when you have a radar, you are sensing the environment by a wave field. So the wave field is continuous by itself. So when you try to estimate the time of delay, in that case you have a continuous time signal that for your convenience you sample, but the time of delay is continuous. So now let's look at this kind of problem, and this is one of many. So I will give you some examples here. So let's consider a continuous time model. The continuous time means that x of t is continuous. So t is a time, and the time is continuous. And then what I measure this x of t within an interval of 0 t, capital T. So that means that, imagine, just to visualize for you, okay? So imagine that, for instance, this is the interval 0, capital T. And in this time interval, I have this delay, this delay, this delay. So I have 3 echoes, okay? So imagine, clapping the hand, tuck, tuck, tuck. I receive 3 echoes by bouncing on the wall, okay? So these echoes, if you remember, we already stated that. So this one is characterized by tau 1 and amplitude A1, tau 2, amplitude A2, tau 3 is amplitude A3. Now, but this signal is continuous time. So it's naturally continuous time. So my goal is to represent this data by having a model, and this model contains the set of parameters theta. Now these parameters theta, in this specific case, is amplitude 1, 2, and 3, and delay 1, 2, and 3. Okay, so in total is 6 parameters. Okay, as I was remarking before, we are assuming that we know the number of echoes. Okay, which is not always true in practice, but let's skip this for a moment. Now let's assume also that the noise W, which is superimposed in the data, is white. So it's a temporary white. So what does it mean? It means that W is a stationary white process, Gaussian, and then since it is white, it is characterized by the power spectral density. Remember, the power spectral density is the Fourier transform of the autocorrelation. So since it is white, so the autocorrelation is a delta line. Okay. Now this delta is a continuous time delta. Now the power spectral density, okay, is just a constant. So it is n0 divided by 2, okay, for any frequency. Now, so in this case, in principle, I should take the problem from scratch, and then I can try to derive what I can, and then I can derive the Lagrange function. I can derive the parametric probability of the observation, the Lagrange function, and then I maximize the Lagrange function with respect to the parameters. Well, we try to make our steps in a very pragmatic way. We know how to write a maximum Lagrange for a Gaussian case. We know how to write the maximum Lagrange, when the signals are sampled. Okay, so let's artificially sample the signals. Okay, and in this way we can derive the maximum Lagrange, the Lagrange function, and the maximum Lagrange method. Now, if we make in this way, which is on the next page, okay, but if we make in this way, then the probability density function of the observation, we will prove that depending on the parameter, it's simply the exponential of minus 1 over n0. Remember, n0 divided by 2 is the power spectral density, okay, for the frequency ranging from minus infinity to plus infinity. And then it's an integral between 0 and t. T is the observation window. Okay, so place a very care in practice about the observation window. Okay, so this one is the observation window. Observation window means where you capture your data. Now, anyway, so you know, the likelihood function is the integral between 0 and t, so within the observation window of the data, minus the model parametric with respect to the data, to the square. Okay? So, you know, essentially it's the exponential of the integral of the square error, if you like. So if I need to find the maximum likelihoods, which means I need to maximize this function, sorry, gamma is just a scaling factor so that the integral is integrated to 1, so the area is 1. No, but you know, this scaling factor is not important for us because what we need to maximize that. So the scaling factor is relevant. Now, rather than, you know, maximizing that, I can take the log likelihood, which means, you know, log exponential goes away, and then rather than maximizing minus something, I can minimize just the argument. And then it comes this as a maximum likelihood estimator. So this is a closed form formula for the maximum likelihood estimator. Now, this means that, you know, if I receive this set of signals, then I need to search in this space, and this space of parameter is 3 delays and 3 amplitudes, which is a 6-dimensional space where I need to find this minimum. So, you know, talking easily, that means that there is no closed form, except some very special case. Okay? Now, we will see in 1 second. Now, just to show you what is the way, how to prove this, okay? The proof is in the following. So, since we know how to get the maximum likelihood for a discrete case, so let's take the continuous one and put it back to the discrete case. So, the trick is very, very easy. So, you know, what can I do is the following. What is written here is the following. Okay, look at the sketch here in this upper corner. Now, if I have my observation goes between 0 and capital T. Okay, this is the signal, okay, which I've measured it. This is x of t. Okay. Now, what I can do is I can sample that. So sampling means extracting the signals regularly in time. Okay. So let's consider that this interval is delta t. And so, you know, if I take the interval capital T divided by delta t, there is in total a number of samples that is m samples. So m samples, which are, you know, t divided by delta t. So this is a total number of samples. Now, if I put it this way, you can solve the problem. Because, you know, this comes to be the discrete time. Now, remember, I'm not saying how is delta t. Okay? So that's the trick. The trick is the following, you know, I'm sampling the signal, step number 1. I'm deriving the maximum likelihood estimator for m samples. Okay? And then what I do? In order to get a continuous one, I take delta t and I make it to go to 0. Okay? So if delta t is going to 0, means that these samples are closer and closer and closer, which means, you know, asymptotically, there is no difference between the continuous time and the discrete time. Okay? So this is the way to make this proof. Now there is a technicality on that. The technicality is the following. If I have a power spectral density, which is an n0 divided by 2, okay, now the power spectral density for a discrete one should be limited between 1/2 to 1/2 of 1 over delta t and minus 1/2 over 1 over delta t and 1/2 over 1 over delta t. So I mean writing. Okay, so this means essentially that I take xt, I sample, okay, but before sampling, let me write this way, before sampling, I need to consider as if I have an ideal low pass filter with a band, okay, that goes between -1 plus 1/2 times 1 over delta t and minus 1 over delta, okay, which is delta, which is, you know, is usually called the anti-aliasing, right? Okay, so I imagine that I have this, okay? So now, you know, and what comes out here is I sample, and what I get is xn, okay, it's the sampled one. So now the sampling frequency is 1 over delta t, okay, this is the sampling frequency, so f sampling. But you know, remember, my experiment is temporarily with a certain delta t, because what I do, I take a delta t and go into infinity at the end of the story. Now, you know, that means that if the power, let's use the red. So if the noise here has a power spectral density that is n0 divided by 2, okay, this is the power spectral density of the noise. The power spectral density of the noise here is limited between minus 1 over 2 times delta t and 1 over 2 times delta t, and that is n divided by 2, okay? So, you know, about this one, the power, okay, here, which is sigma squared w, which is the power of the discrete time noise, is simply delta n0 divided by 2 multiplied by the bandwidth, which is delta t. So it is n0 divided by 2 times delta t. Okay. So, which means if I take a delta t as going to 0, the power is going to infinity, which is the singularity that I get. So now look at this sketch, okay? And let me mark this sketch by use a color here, this one, okay? And this is what is written in the proof. In the proof it's written this way. So it says, what I would like to do is that I can start from the power spectrum, from the conditional PDF of the discrete set. The discrete set is obtained by aggregating, put one after the other, you know, all the samples. Okay? So these are the samples that I was describing here. Then the starting point is that the conditional PDF is something that I can write. And so in my conditional PDF I have a sigma squared w, okay, which I can compute. So now, you know, the power spectral density of noise is bounded within the band of blah blah blah. Okay, this sentence is what is indicated by the star, which means, you know, the power spectral density is limited within the bandwidth plus minus 1 over 2 times delta t. And the power is this one, which is what we calculated. Now, considering delta t going to 0, which means, you know, the number of samples is going to infinite, okay? So what's happened is that this sum becomes an integral. Okay, this sigma squared, you know, goes here, and, you know, blah, 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 and it comes out, you know, the Laplace function. This is the Laplace function that we're going to use, okay? So, you know, now we know how to write the Laplace function for a continuous time case. So we know the discrete time, the continuous time, then we are ready to write any estimator. Now, let's make an example. Assume now that this is very simple, you know, we start very easy, then we get complicated. So assume that I have a signal that is amplitude A, then, you know, there is a waveform ST, the waveform is known, and then there is WT, and WT is a white noise. Now in jargon it's called AWGN. AWGN stands for additive white Gaussian noise. Okay? This is the meaning of this sentence, this acronym. Okay? So it means additive white Gaussian noise. Which means, you know, in one word, I describe WT. Okay? So now, you know, I can write the Laplace function as before, and I can calculate the derivative. So if I want to minimize, you know, I can take the log Laplace and then calculate the derivative. So I calculate the derivative with respect to what? Now the parameter is just A. because it's only the amplitude. Now telecom knows this problem very well, because A contains information. Amplitude is pulse amplitude modulation, so it's a particular kind of modulation. Okay, don't be depressed with the others. Okay, so I'm not considering the modulation here, but it's just to recall the interest of the telecom that they have seen this kind of problem many times. Now, probably not framed in this way. That's the point. Huh? Okay, so anyway, so what I do is just I have the log latitude. Okay, the log latitude, and and the parameter theta coincide with the parameter theta. So it's just one number. Huh? Okay, so my gradient, is with respect to A, and I set to 0. When I set this gradient to 0, it comes out that the maximum latitude estimate of the amplitude is simply xt multiplied by st integrated between 0 and t dt. Now this one is the cross correlation between the xt, which is the data, and st, which is the waveform. Okay? Now, so it's cross correlation, is the waveform. Waveform is known, and this is the data. That is cross correlation. Right? Divided by what? Divided by something that is the energy of the signal. And it comes from the analysis, but I mean in a synthetic way, it's just indicated that way. So it's the energy of the waveform, and the energy of the waveform is something that we know. So nice. Now, since this problem is linear in the sense that it's very simple. Now this is very nice to calculate, to use this simple estimator to calculate the performance, to make the analysis of the performance. Now, how to make the analysis of the performance? So, the estimator finish here. Huh? Okay, so how to make the analysis of the performance? Now, when I make the analysis of the performance, what I say is that the maximum latitude estimate is equal to the true value plus delta A. Now, if the mean value of delta A is 0, then the estimator is unbiased. Okay. Now, let's put it this way. Now, what I need to do to reparameterize in this way is the following. So I skip it here. Okay. So what I need to do, I need to take the estimator, and I need to plug into the estimator the model of the ST, which is AST plus WT multiplied by ST integrated in DT. Okay. Look at that. This is this one. So I'm saying, if I make the performance analysis, so I repeat one time, the goal of this course is not to give the method, it's to give you the method, how to estimate, and to give you the performance. So you need to have an idea at what point, what you can get from your estimate. So, and if you can get a closed form solution, and you know what is the mean error or mean square error or any performance metric, then you know what is the performance of the estimator, and this is what you expect. Because about using these parameter and the metric associated to each estimator is important, because you will use in designing a system, a bigger system. So this one is part of a bigger system usually. No, it's not this one specifically, but usually. Okay, so what I do is I take my estimated value, I plug in the model, and then I continue with that. Oh, by the way, there is a division by the energy. Okay. Now, when I continue this way, what's happened is that the deviation of the estimated value with respect to the true solution is equivalent, It's coincident with the cross correlation between the noise, WT, and the signature, ST. Okay? Everything normalized with respect to the energy. Now, once put in this way, I can calculate the expected value of the estimator. Now, the expected value is expected value of A, which is A itself, and then it is the expected value of the second term. But now, since ST is deterministic, since the energy is deterministic, the only expectation is with respect to the noise, because noise is the only random term. So when I write expectation, the expectation is with respect to the noise, is with respect to the random term, which is noise only. Now, since the noise is zero mean, that comes out that the estimated value coincides with the true one in the mean, and then the estimator is combined. Now, let's calculate the variance. Now, to compute the variance, which is something that we have no time, but really, I recommend to check yourself. Okay? And I'm pretty sure that half of you cannot calculate that if not looking at the book. Okay? Now, once I have seen those half of you that cannot calculate, then I will help the half that cannot, because you deserve that to be helped. Now, so about that, I can calculate, as I said, the variance of that. And the variance of that one is by computation becomes n0 divided by 2 times the energy. So, what happens is that the variance on the amplitude is inversely proportional to the energy of the waveform. Now, usually, this ratio, which is energy of the waveform divided by n0 divided by 2, usually the telecom people call it signal to noise ratio. And so synthetically, this is equivalent to 1 is coincident to 1 over SNI. So it's inversely proportional to the signal to noise ratio. Okay? So if the signal to noise ratio is very high, the variance is very small, which means the amplitude is estimated very accurately. Okay? Check yourself. How can I say? Check it. Okay, check it. And if you cannot make it, contact me. Okay, let me know. Don't look at the book. Do it by yourself. Now, this is for white noise, but the life is not white. The life is not only white noise. And we are engineers, and we are very pragmatic. And so, the engineer is very strange because, they work incremental. And so once I know something, I try to apply what I know to everything. Okay, so let's see if I can apply the estimator for white noise to the case where the noise is not white. Okay, because, once I know something, I try to apply what I know to everything. Okay, so I know the estimator for white noise, then, I apply everywhere. A bridge, a window, it's engineered. You will learn to do this way, okay? So anyway, let's make it. So let's behave as engineers. So let's assume that the noise is not white. So if it is not white, it's called color noise in general, okay? So that means that, it is characterized by a certain autocorrelation and a certain power spectrum density. Now, in order to go back and reuse what we know, we need to introduce the concept of whitening filter. So what is a whitening filter? A whitening filter is a magic filter, okay, which is applied to the data and makes the noise white. Stupid, okay? Why? Because, if I can get this filter, okay, then everything that I get you know, is referred to the white noise. So since I know the white noise, then you know I can solve it, right? Okay. So there was a way to say in Italian. I don't know. It's very strange. Anyway, so you know, this is the whitening filter. Is this G of t, which has a Fourier transform which is GF, and GF is 1 over the square root of the power spectral density. Okay. So then I make a small remark later, but you know, so about what is the power, the square root of the power spectral density. So now let's see if this is truly a white noise. So what I do, I apply on the left, on the right, this whitening filter. Because when I apply the whitening filter to the data, I am implicitly applying the whitening filter to the model and to the noise. Okay? Because you know the data is a model plus noise. And so if I apply this filtering, okay, so if I filter now, if I have x of t, and I apply a filter that has, you know, is a Fourier transform which is GF, then the output, which is x tilde t, okay, is referred to any content of xt. And since xt is containing, you know, the model and the noise, then you know for the linearity is applied to both individually. No, so now you know what's happened is that I mean I have this new signal, which is x tilde, and I have a new model, which is s tilde. So the waveform now is not the waveform as before, is a waveform modified by the filter. But since I know the filter because I design, I apply, then you know I know everything about the filter. Plus what? Plus the noise filter. Okay. Now, if I need to prove that this W tilde is white, the proof is simple. You know, it's by the definition because, I mean, since the power spectral density of W tilde is the power spectral density of W multiplied by G squared. So, you know, SW tilde power spectral density is SW multiplied by absolute value of GF squared. Okay? And now, you know, it's trivially to verify that this is equal to 1 for this specific choice. Now, according to that, then my new model is this one, which is simply a pre-whitened model. So this filter that is behaving this way is called whitening filter. Now the concept of whitening is general. Now, let's see if you have an idea how to create a whitening filter for a discrete time signal. Now, what is a whitening filter? A whitening filter, you're working with the OPEX and CAPEX. So you are creating a company. Is it yours? No, okay. If one day you have to work with your own company, which is something that I really would like for you, okay, then you need to work with that. You need to write your own business plans. Now, let me look at that. Okay, so that one says GF is equal to 1 over square root of WF. Okay? Square root. Now, let me say, how? Assume that everything is discrete time. So, you know, because I can rewrite everything as a discrete time. I don't want to make it, you know, xn, blah, blah, blah. So, assume that you have everything for a discrete time. So, how to design a whitening filter? For discrete time. Now the answer is, I would say, stupid. Because you already know how to make it, but you don't realize. Now, how do you represent the power spectral density? You need to turn on the light. There. Better? You see anyway. Okay. So, how do you make the power spectral density? Well, for discrete time, the power spectral density for whatever process, okay, is obtained by the Z transform of the autocorrelation calculated for Z equal AJ2 pi F. Okay? Right? This is, by the definition, power spectral density is equal to the Z transform. I was writing Z and transform. Okay. Of the autocorrelation sequence. Okay? This is what is written there. Huh? Now, but we know that the autocorrelation sequence, okay, has a set of roots. And so let's make it, this autocorrelation sequence. So I give you this autocorrelation sequence, such as the sequence that we discussed last Wednesday. Okay? So I give you this sequence, and now this sequence, has this set of zeros. And then I make roots, and I calculate this set of zeros. Okay? Can do it, right? Okay, so the Z transform has these zeros. Just to simplify. I'm telling you, my goal is not to be precise. My goal is to show you that you know exactly how to make it. Okay? Now, so these are the zeros. So my goal is to make this filter, which is the inverse of the square root of the power spectral density. Okay? So now, what is this? Now, what is that? Let me say, what is that? Okay, that one, can be obtained as a sequence BZ and another sequence B star 1 over Z computed for AJ blah blah blah, right? Okay. So what is a whitening filter? Now we know that the absolute value of the Fourier transform for this is equal to the other, for the special property of the Z transform. So because of that, the whitening filter is trivially kept. The whitening filter, if you want to apply a causal whitening filter, what you do, you choose all the zeros inside in the circle, and all these zeros is the G of F. All the zeros, are obtained as B a minimum phase, okay, from this one I get the G of F, which is equal to 1 over B minimum phase of Z, calculate for Z equal AJ2 pi F. And since that one is minimum phase, it's causal and stable. So I know how to do that. So that's where I need this story of factorization into minimum maximum phase. I need when I want to create a whitening filter. And where do I need this whitening filter? To calculate the maximum likelihood in case the noise is correlated. So now the puzzle, the pieces of the puzzle, what I'm doing, I'm trying to create, I'm attaching the pieces of the puzzle one by one. Okay? Clear on that? If the filter that I'm looking for should be anticausal, perfect. I'm selecting all the roots, all the zeros outside. And then the zeros outside, which are, you know, the opposite around the circle of this one, are exactly corresponding to an anticausal filter, which is stable. Now, let's make a continuous time frequency estimation and a recursive way. Now, so what I need to make a small digression on that. The digression is the following. I need to talk about the modulated sinusoidal signal. Okay, so what is a modulated sinusoidal signal? Specifically, what does it mean, you know, a frequency or phase modulated? Now, a modulated sinusoidal signal means that, you know, I have a phase, a phi of t, that depends on some other signal. Okay? By the way, this was homework number 2 last year. A frequency modulated sinusoid. Okay, that was on the homework number 2. And some of your colleagues solved by using by approximating a frequency modulated signal by a piecewise approximation, and you know they didn't get a good result. And a few of the students last year, they made it with a frequency modulated signal, and they solved it right away. Now, so let's go forward on that. So that means that I have another signal which is called modulated signal MT, which is in some way manipulating the phase. Now, we have 2 different ways of manipulating the phase. We can manipulate the phase directly, so which means that this MT goes to manipulate the phase, or we can manipulate the phase, we can manipulate the derivative of the phase. In other words, that means that the derivative of the phase is called instantaneous frequency. So because the derivative of the phase is the frequency. Huh? So that is the instantaneous frequency. Okay. So, you know, this is illustrating the concept. Huh? So, for instance, imagine that, I don't know, I have a modulating signal that is a sinusoid, and the modulated, this is the modulating, and this is the modulated. Okay? Modulating means is the one which is active. The modulated is the one that is experiencing. Okay? So I have MT, to make it simple, is entering into this, you know, this sinusoid generator, and then, you know, the output is XT. And the sinusoid generator is changing the instantaneous frequency or the phase according to MT. Now this is the principle of frequency modulation or phase modulation. So, you know, just to illustrate the concept. So in case, you know, I'm changing the frequency by these instantaneous frequency, by these sinusoidal signal, what's happening is that, you know, if the amplitude is positive, the frequency is higher, and then you can see, you know, denser. And if the amplitude is lower, the frequency is lower and it is coarser. Okay, so it goes denser, coarser, and so on. Okay. Now, so there is a strong interest to estimate the phase, because if I estimate the phase, I can get the modulating signal. So if I estimated the instantaneous phase, I get the MT, which is the input. Okay? So, you know, in telecom setting, okay, this signal x of t has been propagating over the air, and so is in some way distorted and is affected by noise. So I neglect any distortion and I only look at the noise. So this is my signal. So the signal is only affected by noise. My goal is to estimate the phase. So how to estimate the phase? Now, this model is continuous time. So my goal is to estimate the instantaneous phase, which means the phase within a certain interval. So one question is, how big is the interval? Okay. Now, the interval should be such that within the interval t, the variation of the phase is close to be zero. So if I make this interval capital T that much visually, the frequency of the sinusoid is almost constant. So when I estimate the phase or its derivative, which is the frequency, it is approximately constant within this interval. So what I'm doing, I'm approximating by a piecewise linear approximation, the behavior, the variation of the phase. Now, so let's consider that, my interval t is small enough such that, the modulating signal is not changing. Okay? So now everything then reduces, simplifies to this model. So this model is xt, the data is equal to a cosine omega 0 t plus phase plus wt. Wt is white noise. If it is not white, we can rewrite it. Okay, and we know. So, now in order to write the maximum likelihood in this case, I need to write the likelihood function. Now, when I write the likelihood function, then the likelihood function is by taking. Let me write here because I have no space there. So it is xt minus a cosine omega 0 t plus phase, okay, square dt integral between 0 and t. This is my log likelihood function. And I need to find the minimum. So to find the minimum, what I do, I need to calculate the derivative with respect to the phase. Let's set the derivative. Now when I do this way, so I have 2 times, so the derivative now enters inside, then I have an integral 0 t, then I have a 2 times, then I have the same as t minus a cosine omega 0 t plus phi. Okay. Then close the bracket. Then I have sine omega 0 t plus phi dt. Okay. So this is my, and that is equal to 0. So this is what I need to solve. Right? Which is what is written on top. Now when what I need to do, I need to combine the pieces. So I need to put together this one and this one. Okay. So that one is 1/2 sine of 2 times omega 0 t plus 2 times phi. So it comes out that I have xt multiplied by sine, which goes here, is equal to a 1/2 a sine 2 times omega 0 t plus 2 phi. Now, it is the case that the integral of that is equal to 0. The reason for that is the following. If I make, if I look at what is the integral means that I have 2, double frequency because I have 2 times omega 0. this way. Okay. The interval t is very big, and and I sum a set of positive and negative value, and I integrate that. So I have a positive area, negative area, positive area, negative area, positive area, negative area. And so if my interval 0t is very large, okay, summing all these positive and negative, in the mean, that interval is 0. So this justify this approximation. So using this approximation, it comes out that my estimator is represented by this equation, which is implicit. Implicit means I don't have a phase equal something. I have, it is in such a way that integral between 0 and t of xt multiplied by sine omega 0, t plus phase, in dt should be equal 0. So I don't have an explicit form, and it's implicit, and the phase is implicit inside. So, what I can do in order to calculate by applying the trigonometric rule, I can find that the phase can be written as arcotangent between the cross correlation of xt and sine omega 0, xt and cosine omega 0. And I found a closure form. So that means that any frequency estimator should make something similar. Now, any frequency estimator does not do this. I don't know why I copied twice. Probably it's okay. But any frequency estimator or any phase estimator does not do this. It's not using this equation, even if it's in explicit form. It uses this. Now, let's revisit. What does it mean? It means that, I have x of t, and I have a sine. Then I have an integral. Now, let's make it like the frequency or the phase, the instantaneous phase, 0, is obtained by taking the input, the signal xt, which is coming in. Okay? I have a signal coming in. I'm reading, I'm just copying. So what I need to do is I need to take another signal which is locally controlled. Okay, I control it. So this signal is a sinusoid, and it is sine omega 0 t plus phi. Now this phase is changing. So what I need to do is that if the correlation between these two, how to compute the correlation? To compute the correlation, I need to integrate between 0 and t of everything that I get at the input. And this that I measure is a kind of error. So this error, actually, we write this error depends on phase. Okay? I'm simply copying. Nothing, I'm copying. I'm copying the first equation on the top, on the right, and I represent the equation by a block representation, where every block, for those that are not used to the block representation, every block here is doing the same operation which is mathematically written there. It doesn't want to work. Okay, it works. You see, xt multiplied by sine of blah 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 in dt, integral should be equal 0. But if I do arbitrary phase, okay, that is not 0. So that is different from 0. So what I can do, I can just, have a generator, okay, of sinusoid oscillator, okay, because these exist. It's a sinusoid generator, where I can control the phase. And so what we can do is the following. I'm sitting here, And what I do is, I look at the error, and I can change the phase. I look there, and I change the phase. Right? Until when? Until epsilon phi is going to 0. If it is going to 0, then I got the estimated phase. Clear? I'm just reading the equation. I told you, it's part of the course. Tell you that the equations should not be read by interval between 0 and t, blah, blah, blah. Because if you take a monkey, can read the equation. So you don't need any genius to read the equation. The equation should be interpreted. And so this is what I'm, the way I'm interpreting that one. Is it clear? That's it, okay? Now I can change one interval, so I can change a little bit, and then I can see what's happened there. And see what's happened, okay? So imagine, and here I see this should be 0. If it is 0, I get the value. So imagine, this is the time. Then I change a little bit, and then the error is this one. It's the error. Then I change a little bit, and the error goes there. Then I change, and this is epsilon depending on, okay? And so depending on the value of the phase, this one's changing. I got it. When, by continuously in the sense that I change, at a certain step interval. And the step interval where I change it is t. Okay? So if I keep on changing at a certain point, I get that the phase error is 0. Then it's done. I have the estimated value. Okay? Now, before, the electronics has already seen this as a phase lock and loop, right? Okay, but I'm not calling it that way, not yet. Okay? This is the technological part, which is not necessary for the others. Okay, so when it's the time, I make 5 minutes for the electronics one. Okay. So now, my goal is to learn how to get the error, how to understand what is the performance analysis, what is the accuracy analysis. So in other words, if I go there and say, okay, this is the estimator, actually, if I do this iterative procedure, changing until I get to 0, and of course, it's out of many questions that you don't know, you don't do by hand. So you have a computer which is changing for you, or you make a processor which is changing for you, okay? So you don't do by hand. But out of any question, when you get to 0, you are solving that, which is equivalent to getting the output out of any question. Okay? So when you get to 0, you get this estimated phase, obtained in this way. Now, remember that arc of tangent is between minus 90 degrees and 90 degrees. Right? If you write arc of tangent, you get a value that goes between minus 90 and 90 degrees, which means that is ambiguous of pi, of 180 degrees. In this process, I need to get the arc of tangent, which is reducing the phase between minus pi and pi, not minus pi half and pi half. In order to do that, you need to make a, I don't know in MATLAB how it's called, it's called atan 2, I guess, atan 2, or 6. It's a function which is giving you back the phase reduced between minus pi and pi. Okay? There is a remark on the book, so you can check. This is just a warning for you in case you apply that and you get to desperate, it doesn't work. Okay, say, well, that guy told me something, told me a fake. the guys with me here, it told me a fake. It's not that there is a fake. It's that you need to calculate the active tangent in the proper way. Now, how to make the performance analysis? Okay, so in order to make a performance analysis, you see, I'm trying to tell you how to make a performance analysis without knowing complicated formulas. Okay, I'm trying to tell you how to make the performance analysis by yourself. So what you say is that, I mean, if I have my phase, the estimated phase actually is the true phase, okay, plus an error of phase. So now, what I need to do, I need to separate the estimated value into these two pieces. Okay? And then, I mean, once I get an explicit form of this delta phi, perfect. I know I can calculate the expectation of delta phi, which is related to the bias. I can calculate the variance on delta phi, and which is related to, with the bias to the mean square. So I have a performance metric. Okay. Now, how can I get it? Oh, it's a phi 0. Okay. How can I get it? Now remember, the easy way to make it is you plug in the model into the estimator equation, which means, let me get it, which means here, copy. Here it is. So this is the estimator equation, that one that I just copied. Okay. So what I need to do, I need to plug in here the model. Okay. So I need to plug in here the model. Which is that one. And the second part remains the same, except that in place, instead of phi hat, I have phi 0 plus delta phi. And in place of that, I have equals 0. So this one is the estimator. Is the estimator with isolated delta phi and WT. Who is making the estimator changing, being random? Is only the noise, because the noise is the only random term. So, let's manipulate this form, okay? So I needed to use some trigonometry rules, blah, blah, blah. And then, at the end of that, when I aggregate, I have a cosine W, so I have a cosine sine, and when I have cosine sine, I put together, okay, and then it comes out of this relationship. So this relationship, which is just a result for that, okay, so this relationship is A0 divided by 2 multiplied by T sine delta T, which is, the erratic, the random term, okay, is equal to minus integral 0 to t wt sine omega 0 t dt. So, if delta phi is very small, okay, so for small error, so we make a small error analysis, okay, then I know I get this delta phi, which is approximately equal to that. Now I'm ready to compute the metric. So it's easy now to see that, if I apply the expectation to this one, the expectation is with respect to W. Since W is 0, the zero mean, then the estimator is unbiased, right? Okay. So this way, I got that the estimator is unbiased. Now you might criticize and say, well, we derive everything with a small deviation. So we don't know what's happened, if the deviation are very big. You are right, but most of the case, I try to analyze what's happened when I deviate a little bit from the true solution. And for a small deviation, this one is unbiased. For bigger one, what can I say? Well, for bigger one, some approximation does not hold. So how can I get the bias? My answer? Simulate. You need to simulate. There's another way. So even in this stupid case where you have one sinusoid and you want to evaluate what is the phenomena when I'm considering a bigger deviation so that all the approximations that I made here are not valid, if you cannot do it, you need to simulate. So this is where the simulations are necessary to evaluate the performance where in those configurations where to make it analytically is too complicated. So for sure what is the for sure what is the performance in the case of small deviation. For bigger deviation, you don't know. You need to simulate. So now you don't need to be a genius to say that this one is unbiased. Okay, and you can calculate the variance. So to calculate the variance, okay, so it is in this way. So it's the expectation since it is the zero mean, so the variance is the mean square, so it's calculated as expectation of delta phi squared. Okay. Blah 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 blah, and then here it comes out. It comes out that depends on the inverse of the amplitude, a squared, and the time. So the bigger is the time, the smaller is the variance. The bigger is the observation time, the smaller is the time, is the variance. The better is the estimate of the phase. Look, the time is here. The time is here. So that means that if this block is integrating very long, then the value that I get here is estimated very accurately. Right? So, that's a very powerful result. This is a very powerful result. Now, sometimes a very convenient way to represent this formula is not always written this way, but you can write it this way. This is equal to n0 divided by 2. It is a squared divided by 2 multiplied by t. Okay? Then you can write it as 1 over t times 1 divided by a squared divided by 2 times n0 divided by 2. Now usually the one that I isolate is the power of the signal, which is the power of the sinusoid, is a squared divided by 2. Okay, and n0 divided by 2 is the power of spectral density. Okay, so this is again a signal to noise ratio. So it's inversely dependent on the signal to noise ratio. The bigger, so the smaller is the noise, the smaller is n0, the smaller is n0, the smaller is the variance. Okay, that's what I get here. Now, this one is also a very nice example where you can test yourself. Remember, when you need to calculate these expectations, you're better to keep a different label, T1, DT1, T2, DT2. Don't make it a square. If you make it a square, you never get results. That's an advice. So now, a couple of minutes for our electronics. okay? Because, you know, they're here, they say, you know, I recognize that one, and this one is a phase locker loop. You're right. So, the loop here, by the way, this is not for the exam. It's only is a culture for all the others, and is something that probably is putting everything into the context for the electron. So, you know, this loop, you know, is in practice is closed. And the way it's closed is by this way. So, you know, there is this block, which is a phase modulator, which is also called the voltage control oscillator. You see the electronics, no? Okay. Okay, which is, you know, just a device for all the others, for non-electronics, okay? It's just a device where you enter with a signal in voltage, and you get out a sinusoid with a control frequency, okay? So, you know, you have an oscillator that is controlled by the voltage. This is the voltage. So when the voltage is 0, this one does nothing, okay? So this one is generating exactly the same phase. So this one keeps changing. This arrow keeps changing until the error is 0 and the phase is perfectly matched. Now, the electronics knows quite well that when this one and that one, you know, they generate an integral that is 0, the signal here and the signal there are in quadrature each other. Which means that, you know, if I have a possibility to look at the signals with an oscilloscope is a device that electronics use every day, okay? So they sleep with an oscilloscope on one side, with a multimeter on the other, and with a spectrum analyzer on the other, okay? So, you know, this is what they have. Am I wrong? Use the electronics, right? So you at least you use it very often, okay? If you don't use it, you will use it a lot. So, and then, you know, what you see is that, I mean, the signal input and the signal locally generated by the oscillator, they are not in phase. So they are they're erratic one another. But when they are perfectly synchronized, which means that, you know, if I keep the phase input as a constant and I keep changing asymptotically, which in engineering means nothing. So, you know, after a long time, then, you know, these two signals are synchronized. What does it mean, synchronized? Synchronized means that, you know, if I look at two signals, they are one in quadrature with respect to the other. Okay? And they are synchronized. Okay? So when I'm using a VCO, two signals are not going like that. But, you know, when one is going up, so when one is generating a sine, the other is generating a cosine. Okay? And they are in quadrature. Okay? So for the electronics, when the electronics says these two signals are synchronous, they don't go this way. They are in quadrature one another. Okay. Now, so how this one works? Since, you know, the accuracy, for accuracy I need to have this T to be big, okay? And, but, you know, I can't have that capital T too big, because, I mean, I need to look at a time interval where this phase is not changing too quickly. So, let me go there. You see? So this capital T interval depends how fast the frequency or the phase is changing. So if the frequency is very slowly varying here, then you can take this capital T very big. Now, saying in the electronic word, this means that the band of the modulated signal should be very small compared to the frequency which is oscillating there. Okay. Usually the number is 100 times. No, sorry. I know this. I know a lot about phase lock and loop because when I started my career, when I was young with the young shorts, okay, and I was in the labs in Hewlett Packard. At that time, they were the leading company, the most important company in microwave. And so I was working together with another friend, another engineer, okay, and by trying to develop an idea to make a multiple phase lock and loop. So we were working day and mostly at night, till very early in the morning. So it was very exciting because we had the opportunity to touch instruments that at my age, when you graduate, your maximum, the top of your excitement was to touch those instruments that cost at that time $100,000 or $150,000. So it means a lot of money. And so when we were working on this, I think that in our test area we had about $500,000 of equipment or even more. So that was unbelievable, impossible in the university, and so that was that time. And so at that time I wrote a short book on phase lock and loop, and I've seen that this book is still used in some industry after 30 years. Okay, so if you go in a company, you see this book, okay, it's very small. I think it was 60, 70 pages. And it was, as usually, I try to be very pragmatic, and since I was a kid, okay, so and that book is still used anyway. So at least I saw it a few years ago. And so so this is the system, huh? And this is the control. So this control depends on the phase. So I keep on moving until I reach the average vision. The control, and the control is usually linear, and it depends on what you put there. And this one is, in jargon, is called the phase lock and loop filter. Okay? This block. So let's have a break. Okay?